Okay, let's just start the session. So I'm going to talk about cloud native supercomputing. So yeah, cloud native computing or cloud computing and the supercomputing, they have been kind of a very different approach for different purposes in the historical perspective. But nowadays we are observing like a kind of consolidation or reconciliation or like a unification of this kind of very different approaches because we are now need to support AI inference workload and various kind of accelerated workloads. So traditionally, we have used like many kind of CPU architectures which are designed for general purpose workloads for like many kind of cloud and client computing and embedded systems and enterprise systems. But as the like computation scale and the size of a workload increases and the data to process the size increases, we need to cover both high performance computing and high throughput computing. So historically, high performance computing dates back to like early 70s and 80s to do scientific research and like rocket science and like hard to solve like computations with computers. So it has focused on doing high precision computation with high performance, like how many CPU cycles and how many number of floating point numbers we can process per second. So we have a very long history here, like a program, very old-ish programming language like Fortran, which are still being actively used in scientific computing. But recently, as the like AI workloads are becoming more popular, we are now seeing a new concept of accelerated computing, which is the terminology coined by NVIDIA's Jensen Huang. So in AI workload, we usually use like reduced precision, like FP8 or int8, or even nowadays we are seeing like a single bit quantization for AI models. So the main focus here is to maximize the throughput to like increase the number of tokens produced per second to optimize the cost efficiency of the AI services. So actually these are very, these two approaches look very different and actually have like a very different workload criteria. But now we are observing the like a convergence of these two approaches in the supercomputing, because now many scientific researches and simulations and predictions they began to use AI models to improve the latency and give the like a rough result in a shorter period of time and so on. So now we and also we are we now have like many different AI application in the scientific field and medicals and healthcare and so on. So now we are going to have like a computing infrastructure that is capable of both accelerated computing and HPC optimized supercomputing. So in details, these two approaches have a very different technical requirements. So AI and HPC, we usually have a large scale computing workload with many different design goals like multi-node scaling and maxing out the hardware utilization and dedication of hardware resources to individual jobs and so on. While the cloud native systems for general purpose computing and the web application hosting, microservices, we usually use a generalized standardized hardware for scale out design and make it fault tolerant, highly available, and make it multi-tenancy native and so on. And the networking has very different characteristics. So in supercomputing, we usually need to make an individual computing node to talk to each other for distributed computing, like OpenMP or MPI. And cloud native systems or web services, we usually have to handle concurrent requests from like a larger population outside the cluster or outside the data center. So we call it kind of a north-south traffic pattern, and while we call the supercomputing like inter-networking traffic pattern as a east-west traffic pattern. The problem and the challenge is that AI systems requires both. So AI computation, the model like inference and training, they are itself compute-intensive workload that requires a lot of like data-intensive I/O as well, with distributed coordination between multiple nodes. But they also need to be able to handle incoming traffic, incoming inference requests, incoming like prompts and chat messages to produce the AI processing results. So, we have been working on our Sokoban orchestrator, which is kind of our homegrown job scheduler designed for container native environments to host the AI and HPC-like workloads. But the cloud native ecosystem, which is led by the Kubernetes project, there have been also many different efforts to bridge the gap between HPC workloads and the Kubernetes. For example, there is like several works like K-Foundry, which tries to merge Slurm's REST API and the Kubernetes API via KCP project, which is a Kubernetes control plane of a control plane project. And also there is another approach called the Supernetes, which provides a bidirectional synchronization between HPC jobs and Kubernetes job paths in virtual kubernetes. So in this case, they don't spawn the actual containers for Kubernetes paths, but they makes like a proxy objects representing actual HPC jobs created in the Slurm cluster. And recently, the official Slurm development company, SCADMD, they have announced the Slinky project, which provides a dedicated Slurm operator for Kubernetes that controls the life cycle of paths like in Slurm, and using some custom resource definition mechanism. And inside the Kubernetes, they also have added many new features to handle AI accelerated workloads in a better ways. Like the most recent release of Kubernetes, version 1.34, released in late August, they added dynamic resource allocation that makes it possible to specify fractional GPU slices and other custom vendor-specific resource requirements in a more generalized way. And the upcoming Kubernetes 1.35, they will add the basic support for gang scheduling for pod groups with customizable workload scheduling architectures. And actually, last week I also attended to the KubeCon last week in Atlanta, and there was Google's keynote about the future roadmap of Kubernetes, saying that they are going to embrace different scheduling frameworks like Slurm and Ray instead of replacing them to make it everything cloud native. So in Backend.AI, we have built our own Sokoban orchestration engine, which doesn't use Kubernetes but uses our own implementation of the batch job scheduler. We are also going to evolve it to Kubernetes native engine, just like how Slurm is being integrated to Kubernetes ecosystem. So this is a very long table. I'm not going to go over the individual items. So we actually have a very similar mapped concepts in Sokoban orchestration engine. For example, we have sessions and corners that corresponds to pod and pod groups, and also we have a fractional GPU resource representation that can be mapped to dynamic resource allocation in Kubernetes and so on. So Actually, we already built and resolved many kinds of resource allocation and fluidization and problems on our own, and now we can map those concepts to the Kubernetes ecosystem. And yeah, so Command already has its own the accelerator device plugging concept and the generalized resource slots to represent the fractional resource slots or unique resource slots, or like unified memory architectures for like DGX Spark or DGX JSON Orient architectures. We do have all those mapping features that is now like coming into the Kubernetes world, but actually we have implemented this in like 5 or 6 years ago. And we also have many features mapping to Slum, which is like kind of de facto standard batch job scheduler in the Supercomputing community. So we are now in the progress of designing Backend.AI running on top of Kubernetes to bring our excellence of the batch job scheduler for AI and HPC workload, which can host many different type of interactive inference and batch workload at the same time. So the first thing we are going to achieve is a transparency to and observability to the existing Kubernetes tooling, so that customers on management tools can seamlessly I found that my mic is missing. Sorry. Yeah, and yeah, make it available to our customers. And yeah, still we want to keep it working with our performance and hardware acceleration, just working like a native Supercomputing project. And but we are still tinkering with which direction will be the best way to integrate, like Kubernetes, like proxy workload management, or Slinky, like a more deeper native integration, or just piggybacking on top of the latest Kubernetes features like DRA. So we also need to consider the actual deployment issues on the enterprise customer side. So we already have more than 100 enterprise customers around the world, and we have experienced many difficult issues when deploying air-gapped environment and enterprise environment when customers set up their own hardware and we install our solution on top of that. The major problem is the networking configuration, because unlike the conventional web service architecture, we now have at least like 3 or 4 different networking layers. Where some layers involves like RDMA or Rocky, InfiniBand, or kind of new technology. This becomes a lot more complicated when it comes to Kubernetes, because Kubernetes has its own service fabric based on CNI architecture. So we need to carefully design and separate these networking abstractions to make everything smoothly work. So this is our kind of draft architecture proposal, how we are gonna integrate Backend.AI into Kubernetes, but though this is not finalized yet. And we have other problems as well, like disaggregated serving, which is a big topic in the AI infrastructure area, which is about separating prefill and decode stages of transformer-based inference request processing, so that we can scale and apply appropriated AI accelerators or chips to optimal stages. For example, prefill stage usually requires a lot more computation power, more like a FLOPS power, while decode stage is bottlenecked by the memory bandwidth. So it is better to use like HBM enabled AI accelerators in the stage. So we can combine these different type of AI accelerators and scale them separately to achieve the maximum efficiency. And there is like a famous open source project called LLMD, which is led by Red Hat, Google, and NVIDIA, and so on, which has been launched in last May, like 5 months ago. And we are also going to integrate LLMD on the Backend.AI platform running on top of Kubernetes. And there are many other issues like CNI, CSI, CRI integrations, and also we have been requested by several partners like a confidential computing support for more privacy preserving AI orchestration and application hosting and others. So in summary, we have designed the Backend.AI Supercomputing scheduler for container native batch job scheduler hosting AI and HPC workloads. And now the HPC community and the cloud native community are converging together to host AI workloads alongside the compute intensive conventional scientific workload as well. So on top of this trend, we are going to make Backend.AI even available to the wider community and the wider audience to find the sweet spot of your supercomputing and data center designs. Yeah, that's all for today. Thank you for listening. Yeah, thank you. Yeah, if you have any questions.